Hi, this is Owen Astrachan for Compsci 201 in fall 2024. Quick overview of some aspects of the percolation assignment. You get, when you fork and clone the assignment, a working class named Percolation Default that uses recursion to find whether there is flow from the top to the bottom, an open or a full cell, as discussed in class on Wednesday, and as you can see in the assignment model. It's very similar to the connected asterisks in the blob model program that we discussed in class. There is stack overflow if you have a big grid when you're trying to find the percolation threshold. For the assignment, you will replace recursion with a stack for depth first search, and you'll replace that stack with a queue for breadth first search. You'll write two different classes. And as a challenge, both for engagement points and for bonus points on the assignment, although it's mostly for engagement, you can do the union find algorithm that I'll describe in this video. There's a grid, and in the grid, each cell has a row and a column number. So for example, 2, 4, that's the row whose index is 2. Top left is 0, 0, so we count down 0, 1, 2, and then we count over 0, 1, 2, 3, 4. And if we open that cell, that's what happens in the simulation, the statistical physics. That means it's possible that water could flow through that cell from the top. But if just that cell is open, there's no water flowing. However, if we continue to open, for example, 3, 3, that's the row whose index is 3, the column whose index is 3. Now 2 cells are open. The cell open at the top in the row whose index is 0 will be full. Full meaning water's flowing, because in this simulation, water flows from the top and the system percolates if it reaches the bottom. So 0, 4, since it's in the top row, will be full. And we color that a little bit blue to use the metaphor of water flowing. If we open 1, 4, because that is open, that means if there are any adjacent full cells, the water will flow into this newly opened cell at 1, 4. Since 0, 4 was filled or full, now water flows to 1, 4. But because water is in 1, 4 and 2, 4 is connected, that means water now flows in those 3 cells. And that's what the code does. Each time a cell is open, it's checked to see whether it would become full, and then its neighbors might also become full. Let's look at how that code works. So if there's an open cell, then this code will check to be sure that it wasn't previously open, because we turn on cells at random in the code. So this says, if it's not blocked, meaning it hasn't been seen, return. Now I know it is blocked, so the code proceeds and it just updates statistics. The number of open cells is updated. The fact that this particular grid cell at row col is updated, and the update on open method is called. That's the method that will check to see, is there an adjacent full cell? Meaning water will now flow into this one. If it's just open and it's not adjacent to a full cell, no water will flow. Here is the update on open method. If it's in the top row, then we know it's full. And that means we're going to search from this cell because it's possibly adjacent to other cells, which will in turn become full. So what happens is, since this is full, this update on open call will call the method search. And search is the method that will be recursive in the code you get, and then will be either with a stack and depth first search, or a queue with breadth first search, or the challenge union find. So top row, it's now full because it's in the top row, so we call the method search. The other way it could be full, this newly open cell, is by being adjacent to a cell that's already full. So if it's a neighbor of a full cell, we need to search from it because now it will in turn be full. And the way we do that is to create a series of offsets. The RD stands for row delta, CD stands for column delta, and what this says is the first values, for example, the ones at index 0, say the row delta is -1 and the column delta is 0. That means it's the row above in the same column. And continuing, we see the next one will be the same row and a column delta of -1. That's 1 to the left. And then we have same row and a column delta of 1. That's 1 to the right. And the final with row delta of 1, that's 1 below in the same column. So this code takes the row and the column that have now been open and looks at the 4 neighbors. In the recursive call, and we'll see that soon, we made 4 different calls, but here I'm looping over the 4 adjacent cells. For example, if row col are 3, 3, the adjacent cells will be 2, 3, that's 1 above, and then 1 below, and then left and right. So we check now to make sure that this neighboring cell is actually an existing cell. So if the new row and the new column, that's NR and NC, those are adjacent cells. If it's inbounds and it's full, then this cell is full. We know this cell has just been opened because this is the update on open method. So if it's adjacent to a full cell, we call search again. And here's search quickly. If it's already full and it's not open, we're going to leave, because search is only called when an open cell is about to be full, because either it's in the top row or because it's adjacent to a full cell. So if it's going to become full, we mark it as full, and then we do this simple recursive calls of saying, okay, mark and search from the row above, the row below, the column to the left, the column to the right. And in order, on 154, we see that's the row above, same column. And then on 155, we see same row, 1 to the left, column -1. And then same row, 1 to the right. And then the row below in the same column. That will help you understand the code you're going to write. When you actually complete the project, you're going to make a new class, Percolation DFS. You will read in the assignment write-up what class it extends, and you will just override search in this new class you create to use depth-first search with an explicit stack. And you'll need a constructor too. As a class invariant, consider that cells that are adjacent and open but not full are on the stack. That's the recursion that we just saw, but now the stack will be explicit. And you can look at the blob code, because there was an example of using an explicit stack in that code as a model. So when you pop the cell, you know it's open but not full. So we're going to check in the neighbors, mark it as full, and push them onto the stack, the same way we did in the previous search method that was recursive. Percolation BFS, or breadth first search, just replaces the stack with the queue. Once your stack code works, the queue code will be very similar. Instead of creating a stack, you'll create a queue. There'll be a constructor in which you create that queue, and then the similar invariant as with the stack. The cells that are adjacent and open but not full are on the queue. You check the neighbors and you add to the queue. The last thing that you are asked to consider doing is a challenge activity with the union find data structure. The union find data structure is also called a disjoint set data structure. Disjoint because initially you start with n distinct or disjoint sets. And to make conversation about them possible, we'll assume that these sets are labeled with integers 0, 1, 2, up to n-1. So we have n distinct, disjoint meaning they don't overlap sets. And the union find data structure allows us to do 2 things efficiently. 1, create a new set from 2. That's the union. So union 2 sets. And what we'll do is we'll take the 2 numbers of those sets, say 2 and 15, and now they're in the same set, and we'll use one of those numbers, 2 or 15, as labeling the new set. But it now has 2 numbers in it. And we can find what set a number is now in, because as the result of a union, a set that was initially distinct might become part of another set. So the find operator or method gives us the set containing a specific number. That's a parameter to the find operation. Initially, their find will return 2 for 2, 3 for 3, and 22 for 22 because each set is in itself and only in itself because each set is distinct. But after unions, a number might be in a new set. Here's how that might work. We're going to have each grid cell correspond to a set. So here we see that the connected cells in the upper left correspond to the numbers 0 and 1, and because they're adjacent and open, they will be in their own set, either numbered 0 or 1. We see in this grid diagram cells numbered 3, 8, 13, 14. Those are also in one set because of the union of, say, 3 and 8, and then 13 and 14, and then 8 and 13. We don't know the order in which the cells were open, but each time a cell is open and adjacent to an already open cell, they become part of the same set. We see down here that there are 3 grid cells numbered 15, 20, and 21 that are also now part of the same set. Now, if you look carefully at the white and black markers in the left, you'll see that the cell numbered 11 is by itself and open. Similarly, the cell numbered 17 is open in a set by itself. But we don't show those in the diagram because they're by themselves. Here, we can see that the white adjacent cells in the bottom right have also been unioned. And if we did a find, for example, on 24, we'd get the number of the set that's now shaded in yellow. How does this work in more detail? There is still a grid indexed by row and column, and the grid cell will be true if it's open. We're no longer using blocked, full, and open. We're just considering a grid of Boolean values that is true if the cell has been opened and false otherwise. When we open 3, 3, that is the grid cell at row 3, 0, 1, 2, 3, and column 3, we'll see that that corresponds to opening 18 because each grid cell is part of a set and those sets are identified by a number. If we have, as in this diagram, 1, 2, 3, 4, 5 by 5, 25 different cells, they'll be numbered 0 to 24 as you can see in the diagram on the right. So if we open 3, 3, now shaded in yellow, that means we're opening grid cell 18. There are 2 virtual cells, V top, that's the virtual top, and V bottom, that's the virtual bottom. I'll explain those in the slides that follow, but the general idea is there is a cell, and it has to be a number that's not on the grid. So typically V top might be -1. And there's a cell that's not on the grid that's at the bottom. That might be n squared because that's not a valid index. The valid indices are 0 to 24. So how does this work? Well, here's the same diagram, and we're going to see more precisely what happens when a cell is open. So if we look in this diagram, we see that cells 13, 17, and 23 are already open. We can see that in the diagram on the left, that course where the cells that are numbered 13, for example, and then 13 corresponds to the blue that's at the bottom of that L-shaped figure on the right. 14 is 1 to its right, and then 8 and 3. We can see that if we open 3, 3, that corresponds to the set 18. We do that with a simple calculation of take the row, multiply it times the grid size, that's 5, and add the column. So we can see that on the bottom left of this slide. We already know that 13 and 17 and 19 and 23 are all adjacent to 18. And I'm about to open 18 because in this diagram, we opened the cell at 3, 3, which corresponds to 18. That means 18 will be unioned with 13, which is already open, union with 17, that's already open, and union with 23, that's already open. That means they 18 will now be in the same set as those cells. But those cells are already in a set that you can see in the diagram is connected to VTop through some previous union operators and to VBottom. So because VTop is connected to VBottom, that means they're in the same set. Connected is just another word for it, in the same set. That means the system percolates. Let's look at an example in a little more detail after we look at what the Percolation Union Find class provides. There are two interfaces in it. One is the finder, and this class itself implements the iPercolation interface that all the classes do. But it's constructed with a specific kind of union finder object because there are various degrees of efficiency depending on what union find algorithm you use. And that's really outside the scope of this challenge activity because we're giving you several union find classes. What this does is initialize the finder with a grid that's size by size plus 2. The plus 2 in this code is for VTop and VBottom. And you'll have to figure out that VTop is likely -1 and VBottom is likely n squared. What happens, for example, in these methods, which must be provided by the interface for percolation classes? There's open, and you simply look to see, is the Boolean value in the grid cell open? That tells you that it is open. Now, is full means the water is flowing into this cell. In the previous versions, that was a value stored in the grid. But here, we simply see, is this specific cell connected to VTop? That's what it means to be full. It means that water's flowing. So we see that connected is find to see whether the same set number is associated with the cell, row call, and VTop, which is a set index. So there's a helper method here, get index, that essentially, just as a reminder you saw on a previous slide, was row times grid size plus call. I prefer to use the helper method to isolate that dependency. Finally, does a system percolate? Yes. If the virtual top and the virtual bottom are in the same set, if they're connected, the system percolates. Here's a little more detail in an example. I'm going to run through what happens when you open specific cells. So first I'm going to open 2,4. That's the code that uses a row and column, but in the union find implementation, we have to find the set that's being opened. So the grid cell 2,4 corresponds to the set 14. So what happens is turning on 2,4 actually makes that number on. Opening 3,3, 3 times 5 plus 3 is 18. That's set 18. So in the grid, we're just setting values to true, but as we'll see, when adjacent cells become connected and open, we'll do a union operation. So now I'm opening 0,4. That corresponds to set 4. And because it's in the top row, it is full. What do we do to mark something as full in the union find operator? Well, what we do is union it with the set that VTop is in. The connect method is what we use in this API to indicate union. So 4 and VTop are now in the same set. Their sets have been unioned. Now I'm going to open another cell at 1,4. That corresponds to set 9. We can see that being open. But now the search operator will say, well, I just opened 1,4. That means I'm going to have to connect 9 and 4 because 4 is already full. And that means I'm going to have to connect 9 and 14 because if 9 is full, then 14 is full. So you'll see that when a cell is open, its neighbors are checked to see if they're full, and if that's the case, they're unioned. Now I'm opening a new cell at 4,3. That's set 23, and because that's in the bottom row, I'm going to have to connect that to the virtual bottom set. So I union or connect set 23, which corresponds to grid cell 4,3, with the bottom. There's a lot of information in what's going on here. I encourage you to think about this carefully, perhaps play it again, as if you want to understand how the union find data structure works to complete the challenge activity. Finally, I'm going to be connecting 23 and 18 because they're adjacent. There's where we are, and union find operators will continue to be executed as we open cells at random in the statistical physics simulation. When does the system percolate? When there's a path from the top to the bottom. That means cells are open in a path from the top to the bottom. Adjacent cells are in the same set, so we can see if VTOP and VBottom are connected. Do they have the same number? When you open a cell at row call, there is no recursion, there's no stack. You check the neighbors, and if the neighbors, and remember there's a set, so you convert the neighbors to a set, then you union the neighbors, and VTOP and VBottom are also sets, so a top row or a bottom row will have to be unioned as well. Enjoy. As you do this, the union find implementations aren't something you have to pay attention to, but just to illustrate the differences, you want both union and find to be efficient. And this is outside the scope of what we do in 201, but at the bottom of the slide, you can see that easy, medium, and harder algorithms. That doesn't mean harder to implement, it really means harder to understand. The easy are linear, the medium are logarithmic, and the harder, which uses path compression, is essentially constant time. And to be fair, from the theory point of view, it's not actually constant time, but in our universe, it turns out to be that way. You can use the Wikipedia entry for union find to see what path compression with a weighted union does. As a reminder, there are n squared disjoint sets, actually n squared plus 2. So these linear algorithms at the bottom, that's when n sets, but they're n squared sets, so it's O of n squared, O of log of n squared, but that's still log n because of properties of logs, and constant time is what it is, constant. There you go. Enjoy.